Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashudu Mamburu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. So today, we'll be focusing on chemical change. The topic is chemical equilibrium. So I think you're going to enjoy the lesson, and there's a lot to learn. And we have the popular KC calculations that we'll be doing. So I'm hoping that after this lesson, you'll be ready to deal with this question of chemical equilibrium. Now, without wasting time, taken straight from the exam guideline, the lesson objectives. This is what we must achieve by end of this day. You must be knowing all this which we are going to talk about here. So it's important that we move together. I hope you have a pen and a paper, you have a calculator, because we'll be doing some calculations as well, and you will be taking some notes when I emphasize stuff here. Now, let's look at the first thing, which is explain what is meant by open and closed system. That is the first thing that we must look at, open and closed system. To say the open system, what is the open system, what is a closed system, what is a reversible reaction, what is chemical equilibrium, and you list the factors. Remember, we say define. So we define open system, we define closed system, we define a reversible reaction, you define the chemical.
2, 1, your life.
Do you know that you are different? Do you know that your fingerprint is different? It's different from your peers, from the people that you are studying with. So do not compare yourself with your peers. Do not compare your results with what they're getting, because you are different. You have your own talents and skills, and also you have your own gifts. Embrace what you can do. Always put in the work to make sure that your results become better than what they were yesterday. But do not compare yourself, because when you compare yourself, you do not know what another person has, and they do not have what you have. So believe in yourself. You are different, and keep on putting the work.
We are still dealing with our lesson objectives, which I am indicating that it is your open system and your closed system, the first two that you must know. Those are the first definitions that we must know. When you say an open system, we're saying this system continuously interacts with its environment. So it's open, it's not closed. But when you say closed system, we're saying this system is isolated from its surroundings. I know when you're busy dealing with paper one, you are saying the net force is equals to 0 there. There are no external forces acting on the system. But when it comes to paper 2, a closed system, we are saying it is isolated from its surroundings. So those are the first important definitions that we must know. The next one is what is a reversible reaction. Remember, you were busy dealing with rates of reactions in the past topic, and then under rates of reactions, our reactions were not reversible. They were running up to completion. But now that we are going to deal with chemical equilibrium, our reactions are going to be reversible. So we refer to them as reversible, and we have a nice sign there that shows that the reaction is reversible, which is that sign there that stands for a reversible reaction. So a reversible reaction, we're saying, is when the product can be converted back to reactants. Remember, under rates of reactions, the reaction was running to completion. We only used one arrow like that. It shows that it's not, the reaction is not, is irreversible. It's not reversible. But now, when you deal with this topic of chemical equilibrium, the reaction must be reversible. In fact, it's one of the conditions for us to reach equilibrium, is that the reaction must be reversible, meaning that we have a forward reaction and a reverse reaction. The second thing, we said this one, the chemical equilibrium, for us to reach chemical equilibrium, it must be in a closed system, which we have defined as a system that is isolated from its surroundings. So you know that there are two conditions to reach chemical equilibrium. The first one was saying the reaction must be reversible. The second one was saying this reaction must take place or occur in a closed system. So it must be a closed system or a system that is isolated from its surrounding. Now, we have as well to know the definition of chemical equilibrium. From the exam guideline, we're defining chemical equilibrium as a dynamic equilibrium. So we're saying it's a dynamic equilibrium when the rate of the forward reaction is equal to the rate of reverse reaction. So we're saying it is a dynamic equilibrium when the rate of forward direction, which I indicated that this is how you'll write the forward direction, the rate of forward direction is equal to the rate of reverse direction. So you can see that the rate of forward direction is equal to the rate of reverse direction. Now, we're as well going to talk about factors that affect chemical equilibrium. Chemical equilibrium can only be affected by three factors. In this case, we're talking about your pressure, your concentration, and temperature. We have a mnemonic there, CPT. That CPT is showing you that is concentration, pressure, and temperature. Those are the three factors that affect the rates of reaction. So you can remember them by saying Cape Town. Then you are able to know that CPT stands for concentration, pressure, and temperature. Remember, with rates of reactions, we said there are 6 factors that affect the rates of reactions. But when it comes to chemical equilibrium, we are saying there are 3 factors that affect chemical equilibrium, which is concentration, pressure, and temperature. So we're going to focus to say how these factors affect the rates of, how these factors affects chemical equilibrium. So I hope that will help us when we move forward. Now, the other objectives, we're going to state Le Châtelier's principle and apply this Le Châtelier's principle. So we're saying, what state Le Châtelier's principle? You will say when the equilibrium in a closed system, remember I said there are 2 conditions for equilibrium, is that the reaction must be reversible and it must be in a closed system. So Le Châtelier's principle is saying when the equilibrium in a closed system, because we can only reach equilibrium in a closed system. So when the equilibrium in a closed system is disturbed, it must be disturbed. When equilibrium is disturbed, the system will reinstate a new equilibrium. When it's disturbed, the system will reinstate a new equilibrium. How will it do that? By favoring the reaction that will oppose the disturbance. So you got to know all those 3 keywords that I've underlined there. To say the first thing is that it is equilibrium in a closed system and it must be disturbed. If it is disturbed, the system will reinstate a new equilibrium. How will it do that? By favoring the reaction that will oppose the disturbance. I can give you a day-to-day example wherein you catch the cold, and then when you catch the cold, you find that your body now is hot. You are having fever. When you touch you are warm. So you feel that the body now is reinstating a new equilibrium. You got the cold, but the body is feeling hot. So you are able to see that there we are dealing with the body that is reinstating a new equilibrium by favoring the reaction. Remember, you catch the cold, then the body is favoring the reaction that opposes, which is the heat. Now, hence you feel more warmer then you are able to see that that's Le Châtelier's principle. It goes in that way. Now, when we say state Le Châtelier's principle, definitely will expect you to state all of that with all the keywords. I'm saying the keywords is the equilibrium in the closed system is disturbed. The system will reinstate a new equilibrium. How will it do that? By favoring the reaction that will oppose the disturbance. So for you to get that 2 marks, you got to state it with all that. The first thing is that the equilibrium must be in a closed system and it must be disturbed. When it's disturbed, a system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. Now, we're going to apply this Le Châtelier's principle to explain changes in the equilibria qualitatively. So we're going to change the conditions there. Remember we said there are only 3 conditions that can change or that can disturb equilibrium. It means it's only when we change concentration, pressure, and temperature that equilibrium will be disturbed. So we're going to look at that. So if it's not concentration, pressure, and temperature, you'll know that equilibrium won't be disturbed because only 3 factors can affect equilibrium, which we said Cape Town. For you to remember, don't write Cape Town in the exam. You must write concentration, pressure, and temperature as the 3 factors that affect equilibrium. Now, we are saying Le Châtelier's principle is going to help us to explain these changes in equilibrium qualitatively. Hence, we are saying you will be able to say what is the disturbance. So if we increase temperature, you will know that the disturbance is that temperature was increased. And if temperature was increased, how will the system reinstate a new equilibrium? We said it must favor the reaction that will oppose the disturbance. So we'll be doing questions based on That one. Now, the other most important thing that we'll deal with is the interpretation of graphs. You must be able to interpret graphs of equilibrium, and then that can be concentration, rate, number of moles, mass, volume versus time graphs. We'll be dealing with that aspect as well. The last part of this lesson will be based on equilibrium constant, calculations of Kc, which is our famous equilibrium constant. And then you will see that the first thing under equilibrium constant, you're expected to list the factors. In fact, it's a factor. There is only one factor that affects equilibrium constant. It is only temperature. Equilibrium constant is only affected by one factor. So if you are to reflect, you are saying we've done rates of reactions. We said there are 6 factors that affect the rates of reactions. When it comes to chemical equilibrium, we're saying there are 3 factors that affect chemical equilibrium: concentration, pressure, and temperature. But now, when it comes to equilibrium constant, which we refer to as Kc, when it comes to Kc, only one factor affects Kc, which is temperature. So you know it's a 6-3-1. 6 for rates of reactions, 6 factors, 3 factors that affect chemical equilibrium, and 1 factor that affect equilibrium constant. Now, write down the expression for equilibrium constant. So you must be able to write the Kc expression when you are given equation for the reaction. And you must be able to perform calculations. So when I leave here, you must be able to say, I know how to write Kc expression. I know how to apply that Kc expression in order to perform calculation based on Kc or concentration values. And you must be able to explain the significance. If you find that Kc is high, what does it mean? If you find that Kc is low, the value of Kc, if it's low, what is the implication? If the value of Kc is high, what is the implication? So this is our focus, and I'm hoping that by end of this day, all this you will be understanding. As we indicated that you have your pen, you have everything with you now. We are taking some notes there and the key points that I'm talking about. Now, let's look at the pre-knowledge. We are simply saying here that you are not empty. You have done already energy and change in grade 11, and you have done already rates of reactions. Now, we are simply saying that now in grade 11, you did these graphs, and then you understand them now, and they will be able to help you. We refer to them as potential energy diagrams. Now, you will remember that for exothermic reactions, we said we are starting with more reactants, but we end up with the less energy of the product. So energy is released when it talks to exothermic. Hence, we're saying exothermic release energy. So energy is released. However, now in chemical equilibrium, we're going now to talk about 2 reactions now. Remember, we said under chemical equilibrium, we no longer have 1 reaction. Remember, in under rates of reactions, we're dealing with 1 reaction, which is the forward reaction that comes to completion. But when it comes to this one now, the reaction is reversible, which means we have the forward reaction and the reverse reaction, which means you look at this graph differently to say, okay, as we move from reactants to products like that, we said that is forward reaction. Forward reaction is exothermic, but as we move from products back to reactants, we will refer to that as reverse reaction. And you can see that the forward reaction here is exothermic, but when you go backward, you see that the reverse reaction will be endothermic. So you got to have that understanding to say when the forward reaction is exothermic, the reverse reaction will be endothermic. So you're able to see that the difference in that in the forward reaction and reverse reaction. The same applies here. The forward reaction, you can see it is endothermic. The reverse reaction will be exothermic. So all the time, when you get a question, you are told that forward reaction is exothermic, you must know that the reverse reaction is endothermic, because at all times we talk about 2 reactions. Remember with our definition of chemical equilibrium, what we said? We said the rate. We said chemical equilibrium, the rate of forward reaction is equals to the rate of reverse reaction. So we have 2 reactions there, the forward reaction and the reverse. Don't make a mistake of saying forward reaction is equals to reverse reaction. We are saying the rate of forward reaction is equals to the rate of reverse reaction. So this is the already the energy that the knowledge that we are having. So sometimes we would indicate delta H is less than 0, as we indicated there. We are saying delta H is less than 0 means that that is an exothermic reaction. Sometimes we just give you a value with a negative sign. You still know that that will be indicating that it's an exothermic reaction. Some on the endothermic part, we can say delta H is greater than 0, or we can just give you a positive value there. You know that it shows that that is an endothermic reaction. So this knowledge, you'll still be applying it under chemical equilibrium. And then we're able to move to say, as we move forward, we're able to say as well, we can deal with the baseline now to say, this is the baseline test that you must be able to deal with as we move forward with these kind of questions. Now, we're saying an exothermic reaction is one in which, so exothermic, but now on this one, we said that there is increase in temperature of the reaction mixture. So you must be very careful when you're dealing with this type of questions, because we are saying now there will be increase in temperature of the reaction mixture. And then we won't have any problem. We're able to see that the answer there will be A without any wasting of time. Now, as we move to the baseline assessment, now the second part, which is now long questions, when we look at what you already know. Now, if you look here, they are saying a single 6.5 gram piece of aluminium metal reacts with 400 cubic centimeter of a 2.6 mole per cubic decimeter sodium hydroxide solution to produce sodium aluminate and hydrogen gas, as represented by the following balanced chemical equation. The first thing that you look at, you are able to see that this is what you have already know. Hence, we are saying this is the baseline. This is the information that you're going to apply even here that you know already. So already you know the meaning of that. It means that forward reaction, that reaction was exothermic reaction. In the case of equilibrium, we'll be referring to it as a forward reaction because there will be a reverse reaction. So we are saying now, you know how to calculate the number of moles. They can say immediately when you see grams here, the mass is given 6.5 grams of aluminium metal. You see that when you have mass, we'll definitely want you to calculate the number of moles. Hence, we are saying now, you know how to calculate number of moles. This is going to be very much useful as you do calculations under the of KC. Now, when you're doing KC calculations, if you are given the mass, you will use that mass to calculate the number of moles, and you can use that mass to that number of moles to calculate the concentration. And then this is very much important. So the most important thing we are saying, when you see the mass, you remember N equals to M over capital letter M, mass over molar mass. So you are able to see that 6.5 you divide it by the molar mass of aluminium, which is 27, and then you are able to say, okay, 6.5 divided by 27, then it's able to give you an answer which is 0.024 moles. So you're able to do the calculation of number of moles. Then we are saying this information, you're going to need it when you deal with KC expression. When you see the mass, you can calculate the number of moles. From number of moles, you can be able to calculate the concentration, which is C equals to N over V. So you're able to see that already. Exothermic and endothermic reactions, because as we talk about temperature, we'll be saying as we increase temperature, which one will be favored, either exothermic or endothermic reaction. So it's important that you know that exothermic is the reaction that release energy. For example, if now you decrease temperature, for example, when you decrease temperature, obviously the reaction that will be favored, the one that must oppose, obviously it will be the one that will increase the temperature of the system, which in this case, it will be exothermic, because exothermic releases energy. Now, how will an increase in concentration affect the rate of reaction? You have done that, the factors that affect rates of reactions. And then you know that as you increase concentration, you increase the rate of reaction. Same thing is going to apply here. Now, as you increase concentration, we are able to draw the graph as well and indicate how increasing concentration is going to affect equilibrium. So it's important that you have that knowledge already to say as you increase concentration, you are expecting the rate of reaction to increase, which means now equilibrium will be disturbed, because we said equilibrium can be disturbed by concentration, change in concentration. And then as you increase pressure as well, remember we said pressure affects only gases. As you increase pressure, you know it will, how will it affect the rate of reaction? You know that as we increase pressure, we increase the rate of reaction. As we decrease pressure, we decrease the rate of reaction. So the very same knowledge, it will be very useful here. Now, increase in temperature as well. You know, as we increase temperature, we increase the rate of reaction. So that knowledge of rates of reactions, it comes in handy here, and it will help you as we deal with questions that will follow. Now, we have our data sheet. We have our data sheet there, which gives us now the number of moles, which is equal to mass over molar mass, and the number of moles as the number of particles over Avogadro's number, the concentration as N over V, or the concentration as C equals to M over MV, and the number of moles as V, with this type of question. Now, I have shown you already that when you are given the mass, you can see I'm writing on the mass there. When you are given the mass there, you will use that formula, which is number of moles equals to mass over molar mass. But you can be given as well number of moles, and you are asked to calculate concentration, or from the number of moles that you calculated, you can be able to utilize it, this C equals to N over V, to calculate the concentration. And then we are saying that you can be given as well the number of particles there. And if you have number of particles, you are able to calculate the number of moles. You can be given the volume of a gas, or be asked to calculate the volume of the gas. So if you are given the volume of a gas under standard temperature, STP, standard temperature and pressure, you are able to know that your molar volume, which is equal to 22,4 cubic decimeter, you applies there. Then you are able to see that you can be able to calculate number of moles by saying volume over molar volume. So this data sheet, you go wherever you're going. As far as you are dealing with paper 2, you will definitely keep it closer, because you will need this to solve questions. Even when you do the case expressions, your calculations, you will be looking at this data sheet, and it will help you to solve problems. Now, we can say chemical equilibrium. Chemical equilibrium, remember we talked about it as a dynamic equilibrium. We say it's a dynamic equilibrium when the rate of forward reaction is equals to the rate of reverse reaction. The rate of forward reaction is equals to the rate of reverse reaction. So you can see on the graph there, the graph is showing you the rate of forward reaction, and the rate forward reaction as the dotted one. Remember, for forward reaction, the rate is decreasing. It's decreasing. We're starting with a very high rate, but the reactants are being used, are decreasing as the products are being formed. So you will see that the reverse reaction starts from 0 there. The forward reaction starts from with a certain value of the rate. So you are having the forward reaction and the reverse reaction. And by definition, we said dynamic equilibrium is when the rate of forward reaction, which we indicated with the dotted line there, is equal. Hence, they become 1 there. You can see they are equal there. Hence, we are saying the rate of forward reaction is equal to the rate of reverse reaction. There, when the graph becomes, the curve flattens, or when the graph becomes horizontal, we know that we have reached equilibrium. I want you to remember that when the graph was becoming horizontal, or when the curve was flattening, when you were dealing with rates of reactions, you said that the reaction has completed or is finished. We said the reason will be the limiting reagent must be used up, or the reactants are used up. In this case, there is no use. The reactants are not being used up, because we are just reaching equilibrium, which means that we are remaining with both products and reactants. The other way to define that will be this concentration graph. So this graph is the graph of concentration. So we are saying the concentration of reactants and the concentration of reactants remain the same. So we're saying the concentration of reactants and the concentration of products remain the same. When we say they remain the same, we're not saying they are equal. We are simply saying that there's no at equilibrium. The concentration of the reactants and the concentration of the products, they are not changing, they are remaining the same. So both these figure 1 and 2 that I gave you there, they all showing you how equilibrium. So you can define equilibrium as that to say it's a dynamic equilibrium when the rate of the forward reaction is equal to the rate of reverse reaction. Or you can define it as a stage in a reaction where the concentration of the reactant and the concentration of the product remain the same. Don't make a mistake of saying the concentrations are equal. It is not the concentration that is equal, it is the rate. So just know that it is the rate of forward reaction is equal to the rate of reverse. But when you talk about concentration, you are saying the concentration of reactants is equal, the concentration of the reactants and the concentration of the product remain the same, which means it does not change. So we're saying in both figure 1 and 2, a chemical reaction has reached equilibrium at T1. So our T1 is that one. You are able to see that at that T1, it means that the graph now is horizontal. So when the graph is horizontal, as you can see on those graphs there, you are able to see that we have reached chemical equilibrium. So we are no longer saying the reaction is completed. We are saying now the reaction has reached equilibrium. And we are saying there are two graphs that you are expecting. It's a graph of rates versus time there, the graph of concentration versus time there. And then we are saying that for those graphs, the graph of rate, the two must be equal. Hence, you see that they now the rate of forward reaction is equal to the rate of reverse. But when it comes to the concentration, we're saying the concentration of the reactants and the concentration of the product remain the same. Now, that's what we are saying there in the explanation, to say when the curves flatten out or become horizontal, after T1, the rate of forward reaction is equal to the rate of reverse reaction. So you can see that when the curve flattens, it means that we have reached equilibrium, or when it becomes horizontal, we are saying that equilibrium has been reached. And then we are saying that the concentration of the product and reactants remains constant. After T1, the reaction has reached a state of dynamic equilibrium. And we have defined dynamic equilibrium where we said is when the rate of forward reaction is equal to the rate of reverse. I hope I have explained to you nicely and you were able to get the understanding of that concept. Now, we are saying you must avoid saying the following. You must avoid saying the forward reaction is equals to the reverse reaction. It's not the forward reaction is equal, it is the rate of the forward reaction. So if you leave out the keyword there, which is rate, then you are not defining equilibrium, chemical equilibrium, because we said a chemical equilibrium is a dynamic equilibrium when the rate of forward reaction, the rate of forward reaction is equal to the rate of reverse. The keyword there being the rate. The rate of forward reaction is equal to the rate of reverse reaction. Please don't say forward reaction is equal to reverse reaction, because that will be marked wrong. And avoid saying the concentration of the forward reaction is equal. The two concentrations are not equal. When you say things remains constant, you are not saying they are equal. No, when they remain constant, it means they are not changing, but not necessarily that they are equal. So when you say the concentration of the reactants and the concentration of the product remain constant, you are saying the concentration of reactants remains the same, the concentration of product remain the same, but you are not saying they are equal. So please don't make a mistake of saying at equilibrium the concentration are equal. They are not equal, they remain constant. Now, the other thing you must avoid saying is to say change in concentration of reactants and products are the same. It's not the change in concentration, it is the concentrations themselves that are remaining constant. So I hope we've explained that and you were able to get it. Now, let's look at this one now, that is dealing with change in temperature. How will change in temperature affect our equilibrium? How will change in temperature affects equilibrium. You will remember we said when you increase in temperature, we said it will favor endothermic reaction. Increase in temperature will favor endothermic reaction. Now, this one you got to know and internalize, because this is the knowledge that we're expecting you to recall when you all the time. When we hear that we are increasing temperature, you must know that it will favor endothermic reaction. So that one you got to know, it stays like that. All the time when say we increase temperature, the first thing that must come to your mind is that when we increase temperature, endothermic reaction will be favored. So a nice one for you to remember is intermendo. Intermendo, to say in there for increase, term for temperature. Increase in temperature favors endothermic reaction. So intermendo stands for increase in temperature favors endothermic reaction. At any given time, when you're asked to say temperature is increased, you got to know that it means increase in temperature favors endothermic reaction. So anytime you are asked or you are told that there is increase in temperature, you will know that increase in temperature favors endothermic before any other thing. That is the first thing that you must remember. But when we decrease temperature, a decrease in temperature, it will favor exothermic reaction. Remember what we said, exothermic reaction is. You remember when you decrease temperature, it means now equilibrium will be disturbed, because you said temperature can disturb, is one of the factors that can affect the chemical equilibrium, meaning that when you decrease temperature, obviously equilibrium will be disturbed. But we said, according to the Châtelier's principle, we said that the system will reinstate a new equilibrium by favoring the reaction that opposes. So which reaction? If we decrease temperature, which action will oppose that? It means that the system must release energy. Again, we said exothermic means energy is released. So because now the temperature was decreased, the one that will be favored is that releases energy. So you're able to see that, okay, when temperature is decreased, it favors exothermic, because the one that releases energy, we said, is exothermic. So when the temperature is released, the system itself now will release energy. It will release energy, the system, which means decrease in temperature favors exothermic. But when we increase temperature, the reaction that will be favored is the one now that will ensure that energy now is absorbed, because temperature is high. You want to make it small down, energy will be absorbed. Hence, we are saying when we increase temperature, endothermic, the one that absorbs energy, will be favored. So you got to always remember. Don't forget, we said intermendo. It means increase in temperature favors endothermic reaction. Decrease in temperature favors exothermic reaction. I hope you have that and it will help you as we move. Now, remember we said we'll talk about three things, which is concentration, pressure, and temperature. I hope you got temperature. You understand that when we increase temperature, it favors endothermic. When we decrease temperature, it favors exothermic reaction. Now we can move to say, now as we are doing that, we are able to move forward to say, now as we change the concentration, as we change concentration, we are saying that now when we increase concentration of the reactants, so we can increase concentration of the reactants and products. And I'm talking here knowing that you know the difference between reactants and product. For example, if I give you a reaction, let's say magnesium, the popular one, solid plus hydrochloric acid to form magnesium chloride plus hydrogen gas, for example, if we give you that equation like that. So you're able to know that if we increase the concentration of hydrochloric acid, which is a reactant, obviously adding a reactant favors the forward reaction. So if we include we increase the concentration of HCl, it means that the forward reaction will be favored because we have increased the concentration of a reactant. But if we increase the concentration of magnesium chloride, which is the product, if we increase the concentration of the product, reverse reaction will be favored. So don't forget, if we are adding a reactant, forward reaction is favored. If we are adding a product, reverse reaction is favored. I hope we are together on that one. The same applies when we decrease. If we decrease now, we decrease, we remove a reactant. For example, we remove HCl or hydrochloric acid. It means that the reverse reaction will be favored. If we remove a reactant, the reverse reaction is favored. If we remove a product, the forward reaction is favored. So you got to know the difference in both concentration and when we change, increase it or decrease it. The last factor that affects equilibrium, we said, is pressure. In this case, we are saying that, remember how we increase pressure. We increase pressure by decreasing the volume of the container. So you can see, as we indicated there, that, okay, if you are having a container of this size, you are able to see if we decrease it, if we decrease that volume, it means we are increasing pressure because you can see the molecules now are placed closer to one another. You have done that when you did rates of fractions. We said increase in pressure, which means decrease in volume. It forces particles closer together. And as you force these particles closer together, definitely you are going to disturb equilibrium. So we're saying if you increase pressure, it favors the lowest or the least number of moles. Don't forget that. If you increase pressure, it favors the least number of moles. So at all given time, you got to know the number of moles that are involved. If, for example, we're having a Haber process, which is N2, which is a gas, reacting with 3H2, which is a gas, to form 2 ammonia gases here. Yes, like that. If that is our reaction, you got to know that the first thing you must do is to check, do we have gases? If no gases, pressure won't affect. So pressure will affect this one because we have gases. But the next thing you must check is how many molecules of a gas do we have on the reactants and how many molecules of a gas do we have on the product. So you can see that on the reactants, we have 1 N2 plus 3 H2. So we have 4 molecules of a gas on the reactants. But on the product side, we have 2 NH3, which means we have 2 molecules of a gas on the product. And we're saying as you increase pressure, it favors the lowest number of moles. So if you increase pressure here, forward reaction will be favored because forward increasing pressure favors the lowest number of moles. So don't forget, the increase in pressure will favor the lowest number of moles, and decrease in pressure will favor the highest number of moles. Please always have that. But there must be gases for pressure to affect. And we are saying if no gas molecules, so there will be no moles of a gas in the reactant. If no gas molecules, equilibrium will not affect. And we are saying if the number of moles are equal, let's say for example you are having A plus B, which is a gas, plus B, hypothetical equation that I'm giving you, forming 2C, which is a gas. So you can see that we have 1A, which is 1 mole, plus another 1 mole. 1 molecule plus another 1 molecule. That gives you 2 molecules in the reactant. And on the product, you are having 2 molecules of C. So you're able to see that the number of molecules are equal of the reactants and the products. If they are equal, you know that pressure will not affect. So pressure affects under these two conditions. When we have gases, there must be gases for pressure to affect equilibrium. Number two, and know that the number of molecules, gas molecules on the reactant and product must not be equal. If the number of gas molecules on the reactant and products are equal, change in pressure will not affect that particular equilibrium. So you know that if they are equal, no effect or no change that the change in pressure will have on that particular reaction. So I hope you got that, and you will remember that as and when we deal with questions, because we're going to do questions there. just to finish what we were talking about, these factors that affect the rates of frictions. Remember, we talked about the first one, which was temperature. We said an increase in temperature favors endothermic reaction. Please don't forget that. I said to you intermedo, which is increase in temperature, temp for temperature, favors endothermic. So all the time when you increase temperature, you know that endothermic reaction will be favored. And we are saying decrease in temperature decrease in temperature favors exothermic reaction. So always know that. But you must note this, that when it comes to rate, because we've done rates of reactions and we are still talking about rates here in under chemical equilibrium. Remember we said chemical equilibrium is a dynamic equilibrium when the rate of forward reaction is equals to the rate of reverse. So we're still referring to the rate. And you know what increasing temperature means. Because when you increase temperature, rate of both endothermic and exothermic reactions will increase. When you increase temperature, it will definitely increase the rate of both. However, we are saying the rate of the endothermic, which is the one that is favored, the endothermic will be faster than that of the exothermic until equilibrium is reached. So it means even when you draw the graph, you will see that the rate of the endothermic when you increase temperature will be high. You'll see that the graph is higher than the graph of exothermic, but all the graph will be increasing because you know that increasing temperature will increase the rate of reaction. The same when you decrease the temperature, it will definitely do the same. Now, when it comes to concentration, we said an increase in concentration of the reactants, forward reaction will be favored, or a decrease in concentration of any of the products favors the forward reaction. So you know that if we increase concentration of the reactants or we decrease the concentration of the products, forward reaction. So forward reaction is favored under, in terms of concentration, it favors and it is favored under these two conditions. The first condition is that when you increase concentration of the reactants, forward reaction is favored. That is the first condition for forward reaction to be favored, is that you must increase the concentration of the reactants. The second condition for forward reaction to be favored is that you must decrease the concentration of the product. So if you decrease the concentration of the product or you increase the concentration of the reactants, all this will favor the forward reaction. And then when it comes to reverse reaction, it means you must decrease the concentration of the reactants or any of the reactants, or you must increase the concentration of the products so that the reverse reaction will be favored. And then we talked about pressure. We said it affects only gases. And we say an increase in pressure favors the reaction that produces the lowest or the least number of moles of a gas. And we said a decrease in pressure favors the reaction that produces the larger amount or the larger number of moles of a gas. I hope you have got, now you understand these factors. And if I must reflect with you what we have covered this far, we're able now to define the open system, the closed system, the reversible reaction, and chemical equilibrium, where we said chemical equilibrium is a dynamic equilibrium when the rate of forward reaction is equal to the rate of reverse reaction. We said this chemical equilibrium can be affected by three factors. And those factors, we said, is concentration, is pressure, and temperature. And we said that this concentration, this pressure, this temperature, they are able to affect equilibrium. But the other factors, for example, that affected rates of reactions, they don't affect chemical equilibrium, because only these three can affect equilibrium. Now we're just explaining how they affect equilibrium. Remember what we said in terms of temperature. We said increasing temperature favors endothermic reaction. Decrease in temperature favors exothermic reaction. We said increase in temperature of the reactant favors forward reaction, or decrease in concentration of the product will still favor forward reaction. For reverse reaction to be favored, we said we must decrease the concentration of the reactant or we must increase the concentration of the product. I hope you got that. When it came to pressure, we said pressure affects only gases. Pressure affects only gases, and then we're able to explain how this pressure affects gases. We said, remember, that when we increase pressure, it means we are decreasing the volume of the container. So we are decreasing the volume. When we decrease the volume, we are saying that pressure increases because you are forcing those particles closer to one another. And then we are saying that an increase in pressure favors the lowest number of moles. A decrease in pressure favors the highest number of moles. So you are able to see that, and then I hope it will help you as and when we deal with the questions that applies to this one. Now, we said we are going to talk to equilibrium constant. We said we are going to talk to equilibrium constant, and then we said this equilibrium constant, it can, the first thing that we talked about, we said only one factor can affect equilibrium constant. We said that factor is temperature. And then we said we must be able to write down the expression for the equilibrium constant. So you must be able to write the equilibrium constant expression, having been given the equation for the reaction. And we said you are going to do today calculations based on the Kc values. And you must be able to explain the importance of high and low values of equilibrium constant. And make sure that when writing Kc expression, you must show the concentrations of the products. I want you to understand that one. You must show the concentrations of products in the numerator and the concentration of reactants in the denominator. For example, if I gave you my favorite equation, which is N2 gas plus 3H2 gas are forming 2NH3 gas. To give you that one, you must be able to write the Kc expression, which we are saying for you to write the Kc expression, you will say Kc is equals to the concentration of the product. We said the concentration of the product must be in the numerator. So, which means now the concentration of ammonia must be in the numerator. And the concentration of N2 and the concentration of H2, these are reactants. Their concentration must be in the denominator. Must be in the denominator. Now, look at this one. Say, remember that the concentration in the Kc expression is raised to the power of the coefficient. So if I said N2, for example, there, you see that the coefficient is 1, which means you will raise it to 1. When you raise something to the power of 1, is as the same as you didn't raise it because it's remaining the same. However, when you are having H2, 3H2 like that, you know that the 3 must be raised to here now to be H2 to the power of 3. So that is important that you have that. And then you add 2 ammonia gas, which means you must raise it to the power of 2. So we're saying the coefficients now, those becomes your exponents. So we're saying like this one, this 1, 3, 2, which is your coefficient or your ratio there. It not inside the case expression, but on top of the concentration. So if you have 2 NH3, you will write NH3 concentration of NH3 to the power of 2. The 2 is the coefficient, not inside, but on top. So it's very much important that you always remember that. And remember this, that the concentration of solid and liquids is 1. What do we mean by that? We are saying that the concentration of solid and liquids remains constant. So it means that if you have a solid and a liquid in the equation that you are given, you will definitely indicate them as 1. And we are saying always represent concentration using square brackets. Always use square brackets. So when you write square brackets like that, it shows you that this you are dealing with concentration. You must know that the yield depends on the temperature change only, hence the value of K. Remember we said Kc can only be affected by temperature. It can only be affected by temperature. So it means if we change the surface area, Kc will remain the same. If we change pressure, Kc will remain the same. If we change concentration, Kc will remain the same. So when it comes to Kc, only one factor can affect Kc. So don't confuse equilibrium constant and chemical equilibrium. Chemical equilibrium, we said there are three factors. It's your concentration, your pressure, and your temperature. But when it comes to equilibrium constant or Kc, it can only be affected by one factor. We're going to do an example where we will do the Kc expression, and I will take you through all those these bullets that I've been explaining here, so that you are able now to have that confidence. But before we do that, let's look at the importance of the Kc value. Remember, we said when you calculate Kc and you get Kc equals to 1, as given there, you must know that the concentration of the reactants, which is the numerator there, the concentration of the reactants and the concentration of the product are equal. So Kc equals to 1, it shows you the concentration of the products and the concentration of the reactants are equal. Then Kc will be equals to 1. When Kc is greater than 1, it means that you have more products. Remember the product at the numerator here. It means now when Kc is greater than 1, it means that more products are formed than the reactants that were used to form those products. So that is a good way of looking at it. Kc greater than 1 means that higher concentration of the products formed than reactants. And it means that forward reaction is favored. Very much important. That Kc value tells you whether the forward reaction or reverse reaction is favored. And it shows you that we have high yield. So the yield of the product will be referred to as high. And the reaction is likely to be economically viable. It means when you calculate the Kc and you get a Kc of greater than 1, you know that this is economically viable. You can continue with that production because the Kc calculation is showing you that you have higher concentration of the products that are being formed than the reactants that are being used. But when you have a Kc of less than 1, it means now that you have lesser products. Remember, we said the products on the numerator and the reactants on the denominator. So if Kc is less than 1, it shows that we have higher reactants. It means we're investing a lot here. Higher reactants, higher concentration of reactants, but we are forming lesser products. Hence the Kc is less than 1. Then we'll say the reverse reaction is favored. And we'll say this means that we have low yield of products and the reaction is likely to be economically not viable. Remember, you are investing more reactants, but you are getting less concentration of products. So it's important to know the importance of the Kc value. I think I've shown you the importance of the Kc value. And then without any wasting of time, I've been explaining. I will give you only 3 minutes. I'll give you 3 minutes break where you will do this calculate. You will write the Kc expression for these following equations that are given here. So these chemical equations, write their Kc expression. Remember, I'm giving you only 3 minutes. After 3 minutes, you must be done doing this activity. I'm saying make all the mistakes, write all the Kc expression, and see whether you understand what you are doing. See you in 3 minutes. Thank you. Thank you. Welcome back. I hope you have written the case expression as expected. Remember, we said for you to do the case expression, you have to first say Kc equals to. It is the concentration of the products in the numerator, the concentration of the reactants in the denominator. So I don't expect you to write Kc equals to concentration of products over concentration of reactant as if that is the equation. At least you just know that on the numerator you will write the concentration of the products. On the denominator you will write the concentration of the reactants. So I will do like that. You know, you are doing math. You know that we have the product. In the first section, our product is HCl. So I'll write the concentration of HCl, which is my product. Remember, we said the coefficients not inside but on top. So you're going to write the 2 there to show that it is raised to the power of 2, which is the coefficient is always raised to that power. So it will be HCl like that. And then you will say H2. Please, learners, don't make a mistake of taking these 2 and raise it to the power. We only raise to the power of the coefficient, which in this case, the coefficient is 1. So please remember that. And you have Cl2 there. So you will write concentration of Cl2. You write it like that is 1, 1. So you will write your case expression like that. I hope you got that. If you got that, you will get 1 mark for writing the correct case expression, meaning that as long as you are doing case expression, you have 1 mark for writing the case expression. This one that I've used for example, so you will get it. You will have said Kc equals to NH3 to the power of 2 divided by N2, concentration of N2, no power because the expression is 1 there. H2, it is H2, you write it to the power of 3. Remember, not inside the coefficient, not inside but on top. And then that is your Kc expression. I hope you got that as well. Number 1.3, you can see, meant to confuse you. Kc expression, what? We have no gas there, but we have aqueous solution. So on the Kc expression, you can only include gases and aqueous solution. So in this case, you have aqueous solution as D. So you will write Kc is D, concentration of the product is D over, remember we said solids is 1. So D times 1 is still, concentration of D times 1 is still 1, divided by 1 is still 1. So Kc is equals to concentration of D. So you'll just write it like that. Because this is 1, this is 1. Remember we said the concentration of solids and pure liquids remains the same. It is 1. So you'll just write Kc equals to D there. I hope you got that. You were able to write the Kc expressions. Remember we're saying under Kc, you will add only aqueous solutions and gases. So by now, you understand, because when we talk about concentration, we talk about concentration of a gas or concentration of an aqueous solution. Hence, even in the Kc, because we're talking about concentration, it will only be gases and aqueous solution. You won't include solids and liquids because we're saying the concentration of solids and the concentration of liquids is 1, remains the same. Now let's do Kc calculation. This is the example that I'm doing, so we're going to do it together, and then I hope you will follow. You are given the consider a hypothetical equation. Remember, we're calling it hypothetical because we're using A, B, C, those alphabets there. Hence, we're saying it's hypothetical because we didn't use your chemicals or your atoms that you get in your periodic table there. If 1 mole of A and 2 moles of B react in a 2 cubic centimeter container, if at equilibrium we have 0.75 moles of C, as from calculate the value of Kc. So they want us to calculate Kc, but we are given 1 mole of A. So this one is 1 mole. B is 2 mole. Initially, remember, initially, as you were doing your rates of fractions, you know that initially you have only reactants, no products. But we can give you questions where we have both reactants and products. But you will have to know that your products will increase because as the reaction starts or as the reaction continues, more products will be formed. So you understand that you will see when we do questions. So we're saying we're at the beginning here, we only had 1 mole of A and 2 mole of B. Means that the product was 0 moles. There was nothing there. Hence, we are saying when you do the KC expression, it's important that you can use the rise table, which is your A. You just copy the equation as it appears, and then you just separate your A, B, C there, which is like that. So I can just say this is A, this is B, this is C. I just wrote it like that, and I did like that. I say this is my rise table, and then it's R, I, C, E. And my rise, because I'm given number of moles here, I must be able to get concentration. So my rice must be cooked. I like to say that, to say, okay, there must be a C there, which is now C for concentration. Remember, concentration is number of moles over volume and is measured in moles per cubic decimeter. Moles per cubic decimeter. So you are able to do that. And then the R there is for the ratio, to say, okay, let's first look at the ratio as given there. So the ratio of the gas there, it will be 1:2:1. That is our ratio. And then the initial number of moles is what we are given. We're given 1 mole, 2 moles, but we know as the reaction starts, we have no product, so that would be 0 moles. So that is 1:1. You got this information from the given information. Another piece of information that is useful is that they are staying at equilibrium. So you got to know that we have this I stand for initial number of moles. In this case, initial number of moles. The C is the change in number of moles, and then the E is for the equilibrium number of moles. So you must know what that rise stands for. Equilibrium number of moles. So we have initial number of moles, change in number of moles, and equilibrium number of moles. And the C is for the concentration. For concentration, we're using the number of moles at equilibrium. So we are taking from equilibrium number of moles, we divide it by volume, we get our concentration. I hope you got that. And then we are able to say, okay, we are given information that at equilibrium number of moles here is given at 0.75 for C. So you go to C and say, okay, C is the product. They are saying we had 0.75 as our product there. Then you are able to see that, okay, remember, when we started, we had 0, but now we have 0.75. What is the change that happened? The change is that we have added to the 0. We have added 0.75. Hence, on the change in number of moles of C, you will write 0.75 as the change that occurred to the 0 when we get 0.75 that we got at equilibrium. So please know that once you get a change, first change, you are able to move. In this case, we got our change, which is 0.75, which is what was changing from 0 to 0.75. The change is 0.75. So once you get the change, one change, you can use the mole ratio to get other changes. So mole ratio, very much important, because we are saying we have 0.75 that represent 1. 0.75 represent 1 mole, and then you want now to get 2 moles. 2 moles will be X. You don't know 2 moles will be X there, which means now that you're going to cross multiply to say 0.75 represent 1 mole. X here will be represented by 2 moles. So the ratio is helping you now to be able to calculate the change, to get the change. The change is in accordance with the ratio. So which means it will be 0.75 times 2. So because it's 0.75 represent 1, X here represent 2, which you cross multiply there, you get 1.5 equals to X. So your X will be 1.5. And then when it comes to A, you said A 1:1, which means for A, the mole ratio is the same. 0.75 is to 1. And let's call it Y. Y is to 1 as well. When you cross multiply, you will see that this, because the mole ratio is the same, it will be 0.75. But remember, the reactants are being used up. So what is happening is that now we were having 1 mole. We used 0.75. What remains at equilibrium? If we had 1, 0.75 was used, it means now you get the change there, which is your difference there, or which will, in this case, it will be 0.25. 0.25, which now is your 1 minus 0.75 is 0.25. Your 2 minus 1.5 is 0.5. So you are able to do that, and then it helps you with your calculations. But remember we said at equilibrium, the concentration at equilibrium, you must only use the number of moles at equilibrium, which in this case will be your 0.25 divided by the volume. The volume they gave us as 2. So you divide by 2, and then you divide 0.5 by 2, you divide 0.75 by 2. It's very much important that you show all that I showed you there, because as and when we mark, we'll give you a mark for the change to say your change is in accordance with the ratio there. So if your change is in accordance with the ratio, definitely you will get that 1 mark. And then you'll get another mark for saying on the product side, you added 0 plus 0.75, it gave you 0.75. On the returns, you say add 2, you used 1.5, you are left with 0.5. You add 1, you use 0.75, you are left with that 1. So it will give you the mark as well for subtraction on the returns and for addition on the products to get equilibrium number of moles. So already you had a mark for your ratio, you had a mark for your addition, you had a mark for your subtraction, and then you're going to have another mark for dividing by volume. So when you divide by your volume there as well, you will get your mark. And then, which all we expect is for you now to start using your calculator to say now 0.25 divided by 2. You will get 0.125. And 0.5 divided by 2, you get 0.25. These are your concentration at equilibrium. 0.75 as well, so you get 0.375. My math is still correct. 0.375 as your concentration at equilibrium. From there, all you expected is to write the Kc expression. So the most important thing is for you to understand this rise table. To say, I will start with the ratio, I will write the initial number of moles that I'm given, I will write the change in number of moles, the equilibrium number of moles, and the concentration. And then you are able to say Kc. Remember, I gave you an activity to do the Kc expression. You will say Kc is equals to the concentration of the product. The product is C. The coefficient is 1. So when it's 1, even if you don't write that 1, it doesn't have any change that it brings. So just write it as concentration of C divided by concentration of A. So the A, the coefficient is 1, so just write it as concentration of A. The B there is 2B, so you can write it as B to the power of 2. So you raise it to the power of its coefficient. And then once you have that, you're going to substitute. So, okay, this is 0.375 for the products for C, 0.375 divided by A is 0.125 to the power of 1, and B is 0.25 squared because there's a 2 there under B. So all you have to do there is to utilize your calculator and you divide, and definitely you will get your answer there for that particular question, which will be your 0.125, and then you're multiplying that by 0.25 squared. And then if you did everything correct, you're able to get your correct answer, which in this case, my calculator is giving me 48. And then you got your answer. Remember, the Kc has no units. So you're able to write Kc equals to 48 there. And that's how you calculate. But it needs you to do more questions. So we're going to do a previous question paper. I think we'll do last year's question paper so that you are able now to follow and see how these questions come in the exam conditions that were in. Now, without any, before that, I would like to talk to the issue of graphs, because without graphs, you might have challenges dealing with questions. So listen to me. If you understand these graphs, you will enjoy this section as well. I think already you see that when you see that the curve is horizontal, when we have horizontal lines like that, the concentration is remaining the same. You are able to see that that is equilibrium. But now, immediately when you see change into those horizontal lines now, they are no longer horizontal. You know that there is a disturbance. And you know that according to the Châtelier's principle, we said that when the conditions of a close of equilibrium in a closed system are disturbed, we said that a new equilibrium will be re-established by favoring the reaction that cancel the effect of the disturbance. So we're going to apply here Le Châtelier's principle, which means now the first thing you must do is to be able to see what is the change, what is the disturbance. You must see the disturbance. And then the second thing, we must see a new equilibrium being established. And we must see whether the forward reaction or reverse reaction is favored. Because to establish a new reaction, we said that a reaction will take place that will cancel the effect of the disturbance. So we want to see all those three. So even when we say use the Châtelier's principle to explain, we would like to see the disturbance, we want to see the new equilibrium being established, and we want to know whether the forward reaction or the reverse reaction is being favored. So I hope that helps you. Now, let's look at ABC. We're saying what is happening at T1. So the first thing we're going to concentrate on T1, and then we're going to say what is happening at T2, what is happening at T3. So we are simply saying at T1, how many chemical species change in concentration instantaneously? So we are saying now, is there any sharp increase? So you can see that if we look there, you will see that at T1, there is a sharp increase in terms of N2. What does that mean? N2 is a reactant. A sharp increase will mean that N2 was added, which means that the concentration of N2 was increased. Interesting. And then we're going to look at how will when that happens, if we increase the concentration of the reactant, we said the forward reaction will be favored. So the expectation is that when we increase the concentration of N2, the forward reaction must be favored. In this case, the forward reaction is the one that forms NH3. And you can see here the NH3 graph is the one that is favored because it's going up. The two are going down. So we're going to, that's what we're explaining in terms of this type of question here. Now, I want us to explain at T1, we said only concentration of N2 increased sharply or instantaneously there, which suggests that this is not a change in pressure or volume. It will otherwise affect the concentration of all chemical species in the reaction. Don't worry about that. And then this is also not a change in temperature, as change in temperature do not change concentration. So I want you to understand those two things. To say, if we change temperature, there will be no sharp increase in any of the concentration of the reactants and the products. So the products concentration and reactants at the moment of change. So at the point there, it means that they will not change, they will remain the same. Only endothermic or exothermic reaction will be favored. So we'll see the favoring, but we won't see the sharp increase or the sharp decrease on the concentration graph. Now, therefore, the change at T1 is the addition of nitrogen gas. So we know that N2 was added, which means we have increased the concentration of N2. And when we increase, remember, if we increase one reactant, the other reactant will be used, it will be reacting with more of the other reactant. So if we increase N2, more H2 now is being used to react with that increased N2, meaning that we're expecting when N2 increases, H2 must decrease. Hence, you see that our N2 is increasing, but our H2 is decreasing. It's decreasing our H2. You can see it's responding. It's saying, no, more of me now, more of H2 is reacting with N2. So you see, sharp increase of N2 shows that N2 concentration was increased, but now the reactants, they start to decrease as more products are formed. So you can see that increase in concentration of a reactant favors the forward reaction. Hence, you see that the forward reaction is increasing, the two are decreasing. I hope I've explained it nicely and you won't forget it. Even when you get it in the exam, you will be able to remember about that one. Now, at T2, so you can see we're having T2 there. At T2, we're saying the concentration of all chemical species of the have increased. So if you check at T2, you have increase in N2, increase in H2, increase in NH3. So when all the concentration increase, you must know that pressure was increased. So when you increase pressure, all the concentrations increase. So you see all of them increased. And so when you increase concentration of N2 only, it was only N2 that sharply increased. But all of them now, N2, H2, and NH3, all the whole graph, there is increase in terms of the concentrations. So when you see all the concentrations increasing, you know that we have increased pressure. When we increase pressure, all the concentration will increase. Meaning that if we decrease pressure, you would expect all the graphs to all go down. So when the graphs are all behaving the same, they're all sharply decreasing or increasing, you know that it must be change in pressure. So in this case, it's change in pressure because all the graphs, they're going upward. Now, change in pressure, because they're increasing, it means pressure was increased. So when you increase pressure, you increase the concentration of all reactants and products. They must all sharply increase when you increase pressure. So I hope you understand pressure. You see, you look at the graph, you are able to see pressure. You look at the graph, you are able to see when one reactant is being increased. Now, we move to the last one now, which is T3. When you look at T3, there is no sharp increase of the concentration of all the reactants and products. Nothing is sharply increasing. Then you know that must be temperature. So when you look there at T3, you are able to see that this must be temperature because there's no sharp increase of all of them. So you're able to see that temperature changed there. But remember, we said forward reaction is exothermic. That which will give you this side, you know that is exothermic because delta H is less than 0. If forward direction is exothermic, reverse is endothermic. So you're able to check which one is being favored. Remember we said intermendo, increase in temperature favors endothermic reaction. And we said increase in temperature, decrease in temperature favors exothermic reaction. So you are able to see there, okay, this temperature, is it decrease or increase? You must check. If we see that NH3 is increasing, which is exothermic, you know that the products are increasing. It means that exothermic is favored. But if you see the increase in N2 and H2, you know that the reverse reaction is being favored, meaning that endothermic was favored, and endothermic is favored by increase in temperature. So in this case, you can see it is the H2 that is increasing, the dotted line there, that small dotted line, and the solid line, which is N2. They are the ones that are increasing, which means we increase temperature because endothermic reaction is favored. Hence, N2 and 3H2 are increasing. So you're able to see that, okay, now increasing temperature favors endothermic. How do we know that? Because the concentration of H2 and N2 on the graph are increasing, while that one of NH3 is decreasing, which means that reverse reaction is favored. I hope you are with me, you are happy, and you will enjoy dealing with the concentration graphs when it comes to chemical equilibrium. Now, without wasting time, we are now in 2024. We are now in 2024, the question paper, to say, let's revise this question paper and see how will you have responded. They say here, initially, an equal number of moles of hydrogen gas and iodine are mixed in a closed container. The reaction reaches equilibrium at a constant temperature according to the balance equation. H2I2 to form 2HI, which is at equilibrium, reversible reaction. Which one of the following is always true at equilibrium? They are saying the concentration of H2 and the concentration of I2 will always be equal. Remember, this concentration depends on the ratio. The ratio is 1:1, which means that if they were equal initially, the change will be equal. At equilibrium, they will be equal. So they will always be equal. Sorry, H2 and I2, because they had same ratio, same initial number of moles. So definitely number A is your answer for this particular question. Now, without wasting time, let's go to the real thing. Now, the question itself, it said the reaction of carbon monoxide. That is it was your question 6 in 2024. The reaction of carbon monoxide gas, CO, with oxygen gas is investigated. The reaction reaches equilibrium in a closed container at a constant temperature, T, in degrees Celsius, according to the balance equation. So we're given 2CO plus O2 to form 2CO2. All of them are gases, so we have no problem. So our factors can work here. Temperature, concentration, and pressure can affect this equilibrium. and then they said delta H is less than 0, which means that this forward reaction is exothermic, which means that reverse reaction is endothermic. Don't forget, when forward reaction is exothermic, reverse is endothermic. Changes to the condition of equilibrium are made at different times. The graph shows the results obtained. X, Y, and Z represent the gases in the above reactions. Now, they say define the term chemical equilibrium. You see, that is your 2 marks. Now, you're going to nicely tell us that this is a dynamic equilibrium when the rate of forward reaction is equal to the rate of reverse reaction. Remember, we said, yes, we do accept if you can define it according to the concentration to say this is in a chemical a stage in a chemical reaction where when the concentration of the reactant and the concentration of the product remains constant. Remember, I said they are not equal, they remain constant. So you're able to get your 2 marks. But I find it much easier when you just define chemical equilibrium as a dynamic equilibrium when the rate of forward reaction is equals to the rate of reverse reaction. But in your mind, you know that at equilibrium, we are saying the concentration of the reactants and the concentration of the products remains the same. Now use the graph to answer the questions below. At T1, oxygen was added. So already they are telling that oxygen was added. You go to the graph, you check that sharply increase. The sharp increase is on X, which means that X is oxygen. Oxygen was added. And I've explained to you that if we increase one reactant, the other reactant, its response is that it will definitely decrease because now more of it will react with the increased oxygen. So CO, we're expecting it to decrease. So the one that is decreasing is CO, which is your Z there. Your Z would be your CO. I find it easier when you just label your entire graph so that you know when you ask questions, it becomes easier for you now to respond. Unlike just working with X, Y, Z, because you will have a problem. So you know that X, your expectation, when one reactant is added, you know that forward reaction must be favored, which is CO2. So CO2 must be Y because it's increasing there, which means forward reaction is favored. So you know that, okay, this one is Y is your CO2. So once you have labeled your graph like that, it becomes easier now for you to respond to questions because questions will be on X, Y, Z. And if you don't know which one is X, which one is Y, which one is Z, you won't answer the question. Let's move. And then they're saying at T1, oxygen was added to the container. Write down the letter that represents oxygen. Obviously, we said oxygen is X because you said it sharply increased. At T2, the pressure was adjusted by changing in the volume of the container. Was the pressure increased or decreased? So you can see that all of them, they are decreasing, but nicely they told us this pressure. But anyway, I think you're going to remember what I told you, that when all the species or all the reactants and products, when their concentration decreases or increases, you know it's change in pressure. In this case, they are decreasing. It means pressure was decreased, which is your question in 313. But in 314, they are saying now, give a reason for the answer to question 3.1.3. So the reason for that answer is that all the reactants and the products, all their concentrations are decreasing. So we have a sharp decrease in the concentration of O2, CO2, and CO. And that indicates that it was pressure that was changed. Because if we change if only one of them decreased, we'll have known that it is one reactant or product that was decreased. But in this case, all of them are decreasing. So you know that it is only pressure that will decrease the concentration of all the reactants and products. Now, 3.1.5, it was write down the name or formula of the gas that is represented by Z. So it's very much important because already I've indicated that that is your oxygen. And then we said, okay, the one that is favored now when we increase oxygen, it is the forward reaction. We said that is CO2 and that is your CO. So when they say Z, you're able to know that Z is carbon monoxide. What would be your reason? You will have said, you have seen it, that when we increase the concentration of oxygen, CO, more of CO was reacting with the oxygen. Hence, you see that the concentration of CO was decreasing there. So what change in temperature, 317, what change in temperature is made at T3? So they are telling you already that temperature was was changed. But even if they didn't tell you and say what is the change there, what is the disturbance there, you will have known that the disturbance here, in accordance with the Châtelier's principle, the disturbance is temperature. Why? Because the concentration is remaining the same. There's no sharp increase in any of the species there. There's nothing that is increasing in terms of the concentration. You know it can only be temperature. Which one is favored? The one that is increasing is your CO2. CO2, so meaning that forward direction is exothermic, because you can see that is forward direction is increasing. So you see CO2 is increasing. So when you for forward direction, we said decrease in temperature, ditto mexo. Decrease in temperature favors exothermic reaction. So you will know that, okay, this is exothermic that is being favored, because you can see that the CO2 is increasing. Then you know that decrease in temperature favors exothermic reaction. So you are saying now, as they decrease temperature, the disturbance, remember Châtelier's principle, you are saying that the disturbance is that temperature was decreased, and a decrease in temperature will favor exothermic reaction. That will always be your second step there. And then you must be able as well to show that, okay, equilibrium was disturbed by decreasing temperature, and then a new equilibrium was reestablished by favoring the reaction that increases the temperature of the system, which in this case is the exothermic reaction. And then you are able to get your marks in terms of that. Now, the one for Kc expression, you were given carbon monoxide gas, CO, which reacts with water vapor, H2O. The reaction reaches chemical equilibrium according to the balance equation. You are having CO plus water forming carbon dioxide plus H2. Initially, you were given 0.6 moles of CO, 0.6 moles of water, 0.1 moles of carbon dioxide, and 0.1 moles of hydrogen gas. This is one of the questions, learners. If now you always thinking that the products will always start initially at zero. In this case, last year paper, initially we had the products as well. So you got to always be careful not to always think that initially the concentration will be zero. So if you're going to use the rise table to use that for that question, you will first write the CO plus your water. They are all gases, and then that is forming your CO2 plus your H2. And then if you do that, you are able to see that now you can divide them and do your rise table without no problem, which we said is the initial ratio, initial number of moles, changing number of moles, equilibrium number of moles, and concentration. Very much important. And then you divide them there. So you're able to do your calculations there. And with no any waste of time, you can simply say the ratio is 1:1:1:1:1, which means your change as well will be the same, because change is always according to the ratio. And then initially you were given 0.6 for CO, 0.6 for water, you were given 0.1 and for carbon dioxide and 0.1 for hydrogen. So you are able now to know that the change there is X, is the same change there is X, 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 X. So the change must be the same. And then you are able now to do your calculations now by finding your change in this case, which will be your 0.6 initial there minus your change 0.6 minus X, 0.6 minus X, and then you are able now as well to do your 0.1 minus X, plus X. Remember the products are being formed. So it will be 0.1 plus X on the product side, 0.1 plus X. So you are able to do all that. And when you are done, remember you must divide by the volume. The volume is of paramount importance. It was 2 cubic centimeter. And then you are able to say that will be 0.6 minus X divided by 2, 0.6 minus X divided by 2, 0.1 plus X. Don't forget, we are adding on the product side. So it's 0.1 plus X over 2, 0.1 plus X over 2. And then you are able to do that. Immediately when you are done with that, you go and write your Kc expression in this case, which is Kc equals to concentration of CO2, the product, plus multiplied by concentration of H2. Remember, there is no plus or minus in the Kc expression. So you can't be adding, you just write the concentrations, which definitely those are multiplications, and then you divide by the reactants, which is your CO and your water there, and then no plus, no minus. So you just write like that. Already you got 1 mark for writing the correct Kc expression. And then you will now come and do the substitution. Remember, you are given Kc equals to 4. So you will substitute your Kc there, which is equals to 4. And then you are able to get now, to substitute now your product, which is 0,1 plus x over 2 multiplied by 0,1 plus x over 2, and you divide by your 0,6 minus x over 2 multiplied by your 0,6 minus x over 2. So very much important now. That's where the signs end. Now you do the maths. You do the maths of cross multiplying. And if you do your serious and correct multiplication, you will solve for x now. That's all you are doing. And then you will get that your x is 0,37. And when you get your x, you are able now to say, I can go and say at equilibrium, I had 0,6 minus x. Remember, we're talking about CO. The question was that you must be able to calculate the mass of CO. So we are looking for the mass of CO. So immediately when you have that, you'll say the mass of CO, of carbon monoxide, is equals to 0,6 minus. For you to the number of moles of this one is 0,6 minus x, which is now equal to 0,6 minus 0,37, which in this case will give you 0,23 as the number of moles of carbon monoxide. You see that? And then the question was calculate the mass. For you to calculate mass, you know number of moles equals to mass over molar mass. So you can simply say, okay, it's 0,23 molar mass of carbon monoxide. Remember, carbon is 12, oxygen is 16. 12 plus 16 is 28. So you are able to get your 28 there, and then you just cross multiply, you get your mass, which in this case, I think you got 0,23. When you multiply it by 28, then you got your 6,44 grams. So that is the question that was carrying 9 marks. So you can see there are different options, hence given the other option there, but because we're showing you with number of moles, and then definitely you will do that. So practice, and don't practice only one way of doing things. There are different options that we can use to solve this problem. Now you, with your phones and your gadgets, you can definitely do the homework. This is your homework. We're hoping that you will be able to answer, and as well, I think you will enjoy it because you have a graph there, and you're going to do your calculations based and answering questions still based on the graph. It has another up to 4.6 there, and then you are able to do this one. We're hoping that you will enjoy doing this activity, that you'll take those pictures and do those activities. And then as I conclude, I will talk to the summary to say today our focus was on the topic chemical equilibrium. We said chemical equilibrium, we defined it as the dynamic equilibrium when the rate of forward reaction is equal to the rate of reverse reaction. We said there are factors that affect chemical equilibrium. We said it is concentration, it is pressure, and temperature. Remember, with temperature, we said we'll look at endothermic and exothermic reaction. We said increase in temperature favors endothermic reaction, decrease in temperature favors exothermic equation. And then we said as well the Châtelier's principle, when the system of a closed system at equilibrium are disturbed or is disturbed, we said now when there is that disturbance, which is the change in concentration, pressure, and temperature, we said a new equilibrium will be reestablished by favoring the reaction that that cancel, or the reaction that opposes the disturbance will be favored. We said equilibrium constant. We are saying to write the Kc expression is the concentration on the numerator, is the concentration of the product raised to the power of coefficients divided by the concentration of reactants raised to the power of coefficients. And we're saying only one factor affects Kc, and that factor is called temperature. Remember, we say the Kc of less than 1 means that low yield. The Kc of greater than 1 means that high yield. A Kc of equals to 1 means the concentration of the reactants and the concentration of the products are equal. I hope you got all that correct. And then we are saying till we meet again, just in time, then we'll meet at 2:30, and then that's what we dealt with. And we would like, without wasting time, to say thank you very much. We are saying anyone who has never made a mistake has never tried anything new. Those are words of Albert Einstein. I hope they inspire you to practice as many questions based on chemical equilibrium as possible. I would like to thank you for watching this lesson. See you next time. Goodbye.